Alrighty, so today is Monday, March 22nd, and we're looking again to finish out the fundamental theorem of algebra. So kind of the big deal with the fundamental theorem of algebra. And if you haven't seen this, look up Friday the 19th video on all of this. But we can take any polynomial function and write their solutions, here's some solutions, as linear factors, and I can write it as a product of linear factors, even with imaginary numbers. So on my video Friday, I solved, or I multiplied out my solutions, writing them as factors, multiply them out to get a polynomial function that gives me roots where they told me the roots would be. So I just want to point out that I can check this with the graphing calculator. So if I go to my y equals, and I type in what I got for my answer, so x cubed, oops, minus 11x squared plus 38x minus 40. They told me that I touched the x-axis 3 times at positive 2, positive 4, and positive 5. Please get comfortable using the graphing calculator to check your solutions or to kind of give you an idea of where to start. So there's 2, there's 4, and there's 5. So my answer is correct because that's where it touches the x-axis at the times that they gave me. Looking at number 2, they gave me the solution 0, 1, and I. Imaginary numbers always come in pairs, so I have a negative I. So I'm going to write these as linear factors. Now, it looks a little strange to write a linear factor with an imaginary number, but it'll be okay. So I have x minus 0. I'm just going to write that as x. And then for 1, I have x minus 1. For I have x minus I. And then for negative I have x plus I. So when I multiply these together, if I multiply the 2 with the imaginary numbers together, my i's will cancel out. So I'm going to multiply these 2 together, I'm going to multiply these 2 together, and then I'm going to multiply those 2 products together. So x times x plus 1, so I have x times x, which is x squared, and then x times negative 1, which is negative x. When I do x minus I times x plus I, it's a lengthy process. And I have weird things, but they'll cancel out. So x times x will give me the x squared. X times I will give me a positive ix. Negative I times x will give me a negative ix. And then negative I times a positive I will be a negative I squared. My ix and my negative ix will cancel out. My negative I squared is negative 1. So this is negative negative 1, which turns into a positive 1. So I end up with my x squared minus x times x squared minus negative 1 or plus 1. When you have imaginary numbers with a positive I here, negative I get a sum of perfect squares. So I need to multiply these 2 together. I'm out of room for this. I'm going to come over here. So I'm going to distribute. So x squared times x squared, that'll be x to the 4th. X squared times 1 will be 1x squared. Negative x times x squared will be negative x cubed, and negative x times 1 will be negative x. So my polynomial function in standard form is x to the 4th minus x cubed plus x squared minus x. If I was to graph this on my graphing calculator, I would only see it touch the x-axis twice because it has 2 real solutions and then 2 imaginary solutions, but it still has degree 4. So let me go back in and check. So x to the 4th minus x cubed plus x squared minus x. All right, so here is my graph. It's still thinking. So there's 0, there's 1. So I have degree 4. I'm not seeing my 2 imaginary solutions, but I have a total of 4 solutions. So it looks like a parabola, but I have some weird things happening down here. It kind of levels off, but only touches the x-axis 2 times. The other 2 solutions will be imaginary. All right, for this third one, I was given the solution of negative 4, and then 2 plus the square root of 3. Well, if I have 2 plus the square root of 3, it came from the quadratic formula. I have to have 2 minus the square root of 3. So refresher, all radical answers and irrational answers will always come in pairs. If they're imaginary, then I have a plus or minus with the imaginary value. If they're radical, then I have a plus or minus with the radical value. So my 2 stays the same. So I have 3 solutions here. So with my -4, that factor will be x plus 4. With my 2 plus the square root of 3, all right, so if I have x equals -4, I need to add 4 to both sides to get x plus 4. So if I have x is equal to 2 plus the square root of 3, in order to make this a factor, I need to subtract 2 from both sides and the square root of 3 from both sides. So my factor will be x minus 2 minus the square root of 3. In this one, I need to subtract the 2, so x minus 2, but I'm going to add the square root of 3. So again, my 2's have the same sign. They're both subtracted because they were added, but I moved them over. And then in front of my square roots, I have different signs. It looks a little gross. It looks a little scary. But again, when I deal with square roots, I promise you, if I give you a square root of the answer, they will always cancel out. So this is a 3 by 3. So I need to multiply it all the way out. It's going to take a minute. So let me just copy down my x plus 4. And then I'm going to distribute. I like to do these one at a time and then line up my terms. So I have x times x, which is x squared. X times -2, which is -2x. And x times the square root of 3, which is the square root of 3x. All right, then I'm going to distribute my -2. And I'm going to write it below with like terms. So -2 times x is a -2x. -2 times a positive, I'm sorry, -2 times a -2 will be a positive 4. And then -2 times a positive square root of 3 would be -2 times the square root of 3. All right, and then distributing my negative square root of 3. Negative square root of 3 times x will be a negative square root of 3x. These will cancel out. Negative root 3 times -2 will be a positive 2 times the square root of 3. These will cancel out. And then negative root 3 times positive root 3 is a negative root 9, which I can simplify. So, canceling out my like terms. So this negative root 9, or minus root 9, sorry, not a negative root, but minus root 9 is the same thing as having a minus 3, which can combine with my 4. So I have x plus 4 times x squared minus 4x, and a positive 4 and a negative 3, so a plus 1. If I was to use a quadratic formula on this, I would get 2 plus or minus the square root of 3. All right, not done distributing, so I'm going to distribute again with my x first. So I have x cubed minus 4x squared plus x, and then distributing my positive 4, so positive 4x squared minus 16x plus 4. So these cancel out. And my polynomial function of least degree with these solutions is x cubed, no x squared, minus 15x plus 4. So I'm going to check this with my graphing calculator. I'm looking for it to touch the x-axis 3 times. One at the whole number value of -4, and then these are decimals, but they're not bad. All right, so I have x cubed minus 15, just a regular old x, plus 4. Okay. All right, so I'm looking for a solution at -4, which I have a solution at -4. Then I have these other two x-intercepts, which are not whole numbers. Sorry, it's hard to see in the light. So this was between 0 and 1, but closer to 0. This was between 3 and 4, but closer to 4. So let me just show you the decimal approximation of 2 plus the square root of 3. It's 3.73, which is this solution here. And then the decimal approximation for 2 minus the square root of 3 is 0.27, which is this one here. So you can get a visual representation. So even though I don't know what these numbers are, I can see what they're between. And then with my radical numbers, it'll get me there. Okay. Next we have the rational root theorem. So this is something to write down. I know it's a little bit vague and a little bit messy. But the rational root theorem helps us find potential solutions. So suppose I have some polynomial with integer coefficients and a non-zero constant. So here I have this polynomial function. So someone asked, what do the subscripts mean? So this is my constant term, a with a subscript of 0, and then a with a subscript of 1, and then 2, and then 3, and then 4, and then 5, and then 6, all the way up to some number n. I don't know what number n is. So if I had something like 5x to the 6th plus 8x to the 5th minus 4x to the 4th plus 6x to the 3rd minus 7x squared plus 2x minus 1. That got really messy. N is 6 because there are 6 items, or it has degree 6, sorry, not 6 items, it has degree 6. So 5 is a with a subscript of 6. So it's just saying the leading coefficient, essentially. And then negative 1 is my a with a subscript of 0. It doesn't have an x, but if I did x to the 0 power, then it wouldn't change my number, which is why we use 0. So it's like starting at 0 and then counting up to the exponent. But all of it boils down to factors of a subscript of 0, which is my constant term, and then a with a subscript of n, which is my leading coefficient, if I put them over each other, then it gives me the factors that are possible rational roots. So, and by rational roots, I mean roots that can be written as 2 and 4 and 5, 0 and 1, but not I, negative 4, but not 2 plus a square root of 3. So this will only show you rational, real, can be written as a fraction solutions. So back in the day, believe it or not, we didn't always have graphing calculators. So you had to guess and check, but you didn't want to guess and check any random number in the whole wide world. You wanted to guess and check strategically using the rational root theorem. So let me show you a couple examples. So for my first problem here, this is my leading coefficient and this is my constant. I'm going to write the factors of each as a fraction as my possible rational roots. So my factors of 6, numbers that go into 6 evenly, are 1, 2, 3, and 6. These are going to be in my numerator, one at a time. My factors of 3 are 1 and 3. These are going to go in my denominator. There will be a total of 8 possible values, positive and negative, so 16 total, because I'm going to take these 4 and put them on top of these 2, one at a time. So that's 1 over 1, 1 over 3, 2 over 1, 2 over 3, 3 over 1, 3 over 3, 6 over 1, 6 over 3. So remember when we did those tree diagrams and we talked about like if you have 3 pairs of jeans and 4 shirts, how many outfits can you make? Same kind of thing here. So my possible rational roots puts all of these numbers over all these numbers in a row. So I like to do them one at a time, starting with my numerator. So I'm going to start with my 1. So I have 1 over 1, 1 over 3. Then I'm going to move on to the 2. 2 over 1, 2 over 3. I'm going to come back and simplify these if I can. Then I take my 3. 3 over 1, 3 over 3. And then my 6. 6 over 1, 6 over 3. So all these can be positive or negative values. You could have positive 1 or negative 1. Positive 1/3, negative 1/3. So I got to list them all out. But let me just clean these up. So instead of 1 over 1, I'm just going to write plus or minus 1. 1/3 doesn't reduce. For my 2 over 1, I'm just going to write that as 2. And then I have this 2/3. For the 3 over 1, I'll just write that as 3. Now my 3 over 3 is the same thing as 1 over 1. So I'm not going to write it again. And I have plus or minus 6 over 1, so 6. And then 6 over 3 is the same as my 2 over 1, so I'm not going to write it again. These are my possible roots. So if I ask you for the possible rational roots, these are them. So back in the day when we used to do some guessing and checking, we would do synthetic division, looking for the 3 solutions. So one at a time, and if I do synthetic division, it brings this down to a quadratic, but I would use these numbers. Today, we do have access for a calculator, so I can graph it and see which ones I should choose, but I still have to show my work. So I'll show you an example of this because I'm looking for 5 solutions here. So for my second example, my factors of 2. Now, good news, I'm using positive and negative numbers, so the fact that this is a -2 really has no effect on me. But the factors of 2 are 1 and 2, and these will go in the numerator. And then I want to find the factors of my leading coefficient, 4, which would be 1, 2, and 4. So 2 on top, 3 on bottom, so it's going to be 6 total. So my possible rational roots include plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 4. And I'm done with the 1, then I'm going to move on to the 2. So plus or minus 2 over 1, plus or minus 2 over 2, and plus or minus 2 over 4. So I'm going to simplify. So positive and negative 1, positive and negative 1/2, positive and negative 1/4, positive and negative 2. This positive negative 2 over 2 is the same as a positive negative 1 over 1. And my 2 over 4 is the same as 1/2. So these are my possible rational roots. So I'm looking for 5 solutions. So if I go to my graphing calculator and I enter this in, so 4x to the 5th minus 12x to the 4th plus 5x to the 3rd plus 8x squared minus 3x minus 2. So I'm looking for 5 solutions. Some of them will come out of this. This is 8 different numbers. Not all of them will be solutions. So I'm going to graph. This one takes a second to graph. It's a high degree polynomial function. There we go. All right, so this graph touches the x-axis 3 times. Do you remember what happens when it bounces like this? And this? Those represent multiplicity. So this number, which is the positive number 1, happens twice with 2 solutions that are identical. Then it crosses through 2. So it's looking like I have negative 1/2, maybe that's negative 1/4, twice, that number twice, positive 1 twice, and positive 2 once. So I'm going to do synthetic division with 1, 1, and 2. If I do it 3 times, my 5th degree polynomial will go down 3 degrees, and I'll have a quadratic x squared. So I'm looking for 5 solutions. 1, 2, oops, I just put in a 1, 2, 3, 4, 5. Make sure you can see them. Okay, I accidentally put a 1 in there. Let me take it out. I'll put it back in, but I don't know yet. All right, so you have to show your work with these kind of problems. You have to show your work. This does not factor by grouping. It does not do a product sum. It is not a special sum or difference of cubes or difference of squares. So I got to do some division. So I'm going to start with the number 1 and put my coefficients. The remainder should be 0. So little synthetic division. Right. And it did work. So x equals 1 is a solution. It had multiplicity, so I'm going to do it again, but I'm going to do it again from this quotient. So this is 4x to the 4th minus 8x cubed minus 3x squared plus 5x plus 2. I went down a degree. Every time you do synthetic division, it's a beautiful thing. You go down a degree. So I'm going to do synthetic division again. I should get a degree, remainder of 0. Since it had multiplicity of 2, it should happen twice. Bring down my 4. 7. All right, and that works. So 1 happens twice. So this is 4x cubed minus 4x squared minus 7x minus 2. With these 4 terms, I might be able to factor, but if I factor by grouping and put together these with a 4x squared coming out, but that won't give me the 7x minus 2. So I'm going to do division again. I've exhausted my 2 ones. So the other whole number that it hit at was 2. So multiplicity of 2. So I did the 1 twice, and I'm going to do the 2 next. And then I should come out with these decimal answers here, these fraction answers. So doing 2, I'm going to do it for my quotient here. Every time you do division, you always want to go down a degree, so you always want to take the previous quotient. Our remainder should be 0, so we're down 4, 4, 1, oh, and then we have 4x squared plus 4x plus 1. This will give me 2 solutions, so 2 did work. So out of my possible rational roots, positive 1 and positive 1 happened twice, positive 2 happened, and then it's either going to be 1/2 or 1/4. So with this trinomial, I'm going to make a product sum chart to help me factor. We could always use the quadratic formula. I just like to factor. So my product is 4 times 1, which is 4. And my sum is 4, so I'm looking at 2 times 2. Now don't forget to divide these 2's by your leading coefficient, which is 4. So this reduces to 1/2, and this reduces to 1/2. I did want them to be identical because it did bounce at that value. So the bottom value goes up. So I have 2x plus 1 times 2x plus 1. That's what this is factored. So if I set 2x plus 1 equal to 0, my x value is negative 1/2 for each of these. Multiplicity, they're identical. You don't have to write them twice, but if you don't write them twice, you do have to say there's a multiplicity of 2. So I found my possible rational roots. I used a graph to help me identify which rational roots I should try with synthetic division. I did synthetic division until I got it down to a quadratic. Right? This is the big theme that we're looking for with solving polynomials. Thanks for watching.